In the digital age, we inhabit a world increasingly reliant on intricate networks of information. Enter computer viruses, self-replicating programs designed to disrupt, damage or gain unauthorized access to our digital lives. These lines of code, often perceived as malicious invaders, share a curious parallel with the biological viruses that plague the natural world. Both are capable of self-replication, spreading rapidly and causing significant harm. Biological viruses, through natural selection and random mutation, constantly adapt and evolve to survive. This raises a fascinating question. Do computer viruses also undergo a similar evolutionary process? Can they learn, adapt, and outsmart our best defenses? Unlike the natural world, governed by the laws of physics, the digital realm is a construct of human design. Every line of code, every algorithm, every digital environment is ultimately a product of human ingenuity. Computer viruses are not products of chance, but carefully crafted tools designed for specific purposes. The very existence of computer viruses hinges on the skills and intentions of programmers who write, modify, and distribute them. This human element sets them apart from their biological counterparts, which arise and evolve through natural processes. The evolution of computer viruses is a controlled process. When a virus encounters a new obstacle, such as an updated antivirus program, its survival doesn't depend on random mutations. Instead, it relies on the programmer's intervention. Programmers release updates and patches, much like software developers do for legitimate applications. This constant back and forth between virus creators and security researchers resembles an arms race, where each side tries to outmaneuver the other.
The digital environment, despite its complexity, operates under strict rules. Computers, unlike biological organisms, are unforgiving of errors. A single misplaced character in a line of code can render an entire program useless. This rigidity imposes severe limitations on the possibility of random beneficial mutations. In contrast to the adaptable world of biology, where mutations can sometimes lead to advantageous traits, the digital world demands precision. Random changes in a computer virus's code are far more likely to break it than to improve it.
Imagine a computer virus's code as a complex machine, with each line representing a cog or gear. This intricate mechanism relies on the precise interaction of its parts. A single misplaced gear can bring the entire machine to a grinding halt. Unlike biological systems, which exhibit a remarkable degree of flexibility, computer programs are unforgiving of errors. A random change is far more likely to break the code than to improve it. This inherent fragility of code severely limits the potential for random mutations to lead to anything but dysfunction.
Unlike biological mutations, which occur spontaneously, changes in a computer virus's code are almost always intentional. Programmers introduce modifications with specific goals in mind. These alterations are calculated adjustments designed to enhance the virus's effectiveness. When a virus encounters a new obstacle, the programmer steps in, identifying and modifying the code segments responsible for detection. This process is akin to a mechanic fine-tuning an engine, making precise adjustments to optimize performance.
The world of computer security is often described as an arms race, a constant back and forth between those who create viruses and those who seek to neutralize them. Antivirus programs, the digital immune system of our computers, are constantly evolving to detect and block the latest threats. Virus creators strive to outmaneuver these defenses, developing new techniques to evade detection. This ongoing struggle drives a cycle of adaptation, but it's not Darwinian evolution in the traditional sense. Viruses don't spontaneously develop resistance to antivirus software through random mutations. Instead, programmers modify their creations to circumvent these defenses. This dynamic, driven by human ingenuity on both sides, highlights the controlled nature of computer virus evolution.
The digital world operates on a language far more rigid and unforgiving than any spoken by humans. Computers possess no intuition, no capacity for interpretation. They understand only the precise language of code, a series of instructions executed with unwavering literalness. This fundamental difference in how computers process information has profound implications for the potential of computer viruses to evolve through random mutations. In the natural world, mutations are the engine of evolution. However, In the digital realm, randomness is often the enemy of functionality. Randomness, the driving force of biological evolution, is often the enemy of functionality in the world of computer code.
Imagine a computer program as a finely tuned machine, each line of code representing a crucial component. A single misplaced character, a missing semicolon, an incorrect command can bring the entire system crashing down. These errors, known as syntax errors, are the digital equivalent of a wrench thrown into the gears of a finely tuned engine. Unlike biological systems, which exhibit a remarkable degree of resilience, modern computer programs are notoriously intolerant of errors. A single syntax error can render an entire program useless, preventing it from executing even the simplest of tasks. However, that should not always remain the same. There may appear new architectures, much more flexible and tolerant to syntax errors. Based on neural networks, for example,
The notion that random changes to a computer virus's code could somehow lead to improvements is a misconception often fueled by science fiction. While it's true that mutations drive evolution in the biological world, the digital realm operates under a different set of rules. The complexity of computer code, coupled with the strictness of its execution, makes it highly improbable that random alterations would result in anything but dysfunction. Consider the vast number of possible changes that could occur within a computer virus's code. The overwhelming majority of these mutations would be either neutral or detrimental, introducing errors that hinder its operation. The likelihood of a random mutation introducing a beneficial change is vanishingly small.
the current digital environment imposes inherent limits on the potential for Darwinian-style evolution. Computer viruses, unlike biological organisms, do not inhabit a world of infinite possibilities. They are constrained by the rules of computer science, the limitations of software and hardware, and the constant efforts of security researchers to neutralize their threats. While it's conceivable that new architectures and sophisticated artificial intelligence could one day create self-evolving computer viruses, that reality is somewhat remote. The current generation of computer viruses in today's computers are essentially tools crafted and controlled by human intelligence.
Imagine a vast desert, stretching as far as the eye can see. This barren image serves as an apt metaphor for the digital environment in which computer viruses exist. Unlike the natural world, teeming with diverse life forms, the digital realm is relatively homogeneous, a monoculture of code. This lack of environmental complexity has profound implications for the potential of computer viruses to evolve through natural selection. In the natural world, organisms face a constant struggle for survival, competing for resources and adapting to ever-changing conditions. This relentless pressure to adapt drives the engine of evolution, leading to the incredible diversity of life we see around us.
The digital environment, while vast and complex, lacks the nuanced challenges and opportunities presented by the natural world. Computer viruses, unlike biological organisms, do not encounter predators, parasites, or fluctuating weather patterns. They exist in a world of ones and zeros, where the rules are absolute and the consequences of even the slightest error can be catastrophic. This unforgiving nature of the digital realm severely limits the potential for random mutations to lead to beneficial adaptations. In the natural world, a mutation that proves slightly detrimental in one environment might prove advantageous in another. In the digital world, however, such nuances are often absent.
The presence of sophisticated security software, constantly evolving to detect and neutralize threats, further homogenizes the digital environment. Antivirus programs, firewalls, and intrusion detection systems act as digital immune systems, actively patrolling for and eliminating malicious code. This constant pressure from security software creates a selection pressure, but it's a pressure that favors uniformity rather than diversity. This drive towards homogeneity, while essential for maintaining the security of our digital lives, further limits the potential for computer viruses to diverge into distinct species with unique adaptations.
The interactions between computer viruses and their digital environment are fundamentally different from the complex interplay of organisms within a natural ecosystem. Viruses do not engage in symbiotic relationships, compete for resources, or experience the gradual pressures of a changing climate. Their existence is largely defined by their interactions with human-created systems, systems designed with security in mind. This controlled environment limits the scope for the kind of emergent behavior and unpredictable adaptations that characterize Darwinian evolution. Computer viruses remain tethered to the intentions of their creators, their evolution guided by human ingenuity rather than the blind forces of natural selection.
The digital world moves at a breakneck pace. Innovation follows innovation in rapid succession, with each new generation of hardware and software rendering the previous one obsolete. This relentless march of progress creates a challenging environment for anything aspiring to evolve through gradual Darwinian-style adaptations. Imagine a species of bird trying to evolve a longer beak to reach nectar deep within a flower. In the digital world, the flower might be redesigned, the nectar moved, or the entire ecosystem replaced with a new, incompatible version before even a single generation of viruses could adapt.
The lifespan of a computer virus is often short and brutal. New viruses emerge with alarming regularity only to be quickly neutralized. This rapid turnover is driven by the constant arms race between virus creators and security researchers. Computer viruses rarely enjoy longevity.
The Red Queen's race. A constant struggle for survival. The digital world is a frantic sprint on a constantly shifting treadmill. Computer viruses must constantly adapt to keep pace with cybersecurity measures. This is the Red Queen's race, highlighting the futility of out-evolving the opposition.
The absence of Darwinian evolution in current computer viruses doesn't preclude new, insidious threats. The digital world is in constant flux. New technologies emerge, new vulnerabilities are discovered, and those who exploit them are ever more ingenious. The future may lie in artificial intelligence, with self-learning algorithms adapting faster than humans. Imagine a virus rewriting its own code, exploiting vulnerabilities faster than they can be patched. This highlights the need for constant vigilance and proactive cybersecurity strategies. Imagine, however, a new computer architecture, one that differs from the John von Neumann architecture of the previous century, based on neural networks, for example. It is known that neural networks are Turing complete. That means they can replicate any computer program known so far. And, with even slight variation of weights in this network, it's a completely new program. It will not crash with a change of parameters. It is very resilient to even large mutations. That could pave the way to self-developing programs very suitable to true Darwinian evolution. It could lead to truly evolving computer programs, viruses, or otherwise. Future architectures like that could bring about a true evolution in computer software. Many wonders could await us then, perhaps even new forms of digital life.